Hey everyone, and welcome to This Explainer. Today we're taking a really fascinating journey inside the beating heart of your computer, the Central Processing Unit, or CPU. I like to think of the processor not just as some cold piece of hardware, but as a highly efficient, incredibly fast manufacturing plant. Literally everything your device does, from rendering a massive high-definition video to simply typing a Word document, relies entirely on this ultimate assembly line, running without a single hiccup.
So ask yourself, what exactly goes on inside the brain of your computer? How does a tiny, rigid little silicon chip function as the ultimate manager of every single digital task you perform? It kind of seems like magic, right? But as we'll uncover today, it's actually just a masterpiece of highly structured organization and logical data flow.
So, here's our roadmap for today's factory tour. We'll start by cracking open the CPU black box. Then we'll look at registers, which are the CPU's own high-speed memory. After that, we'll map out the instruction cycle, explore the completely game-changing concept of pipelining, and finally look at two real-world megafactories, x86 and ARM.
All right, let's jump right into Section 1 inside the CPU black box.
Okay, let's dive into this. Before we look at the factory's workflow, we need to know what our processor is actually hired to do. To function at all, a processor has 5 core requirements. First, it's got to fetch an instruction from memory. Second, it has to interpret or decode that instruction to figure out what action it needs to take. Third, it might need to fetch some extra data from memory to complete the task. Fourth, it actually processes that data, doing the math or the logic. And finally, it has to write that processed data back out. Literally, every single thing your computer does is just a rapid-fire repetition of these 5 steps. So looking inside the CPU, think of the arithmetic and logic unit, the ALU, as the heavy machinery on the factory floor doing the actual physical computation. Over on the right, you've got the control unit. This is like the factory manager, coordinating all the movement of instructions and data. And bridging the whole shebang together is the internal CPU bus, acting as a high-speed conveyor belt that moves data between the manager, the heavy machinery, and the local storage.
Moving on to Section 2, Registers, the CPU's memory.
If the main memory of your computer is a distant, massive warehouse, registers are the individual workbenches right next to the machinery on the factory floor. These workbenches generally fall into 2 categories. On one side, we have user-visible registers. These are out in the open for machine or assembly programmers to optimize their code and save trips to that distant warehouse. On the other side, we have control and status registers. These are mostly hidden from the programmer. Well, actually, they're used exclusively by the control unit and the operating system to safely manage the execution of programs and monitor the state of the processor itself.
And within those control registers, there are 4 that are absolutely crucial for executing instructions. The Big 4. The program counter, or PC, is essentially the manager's running to-do list. It holds the exact address of the very next instruction to be fetched. The instruction register, or IR, holds the specific instruction that's currently being worked on. Then we have the memory address register and the memory buffer register, the MAR and MBR. These 2 work together like a shipping and receiving dock, staging the actual bits of data as they move in and out of the CPU across the system bus.
Let's move to Section 3, the instruction cycle explained.
Now that we know who's on the floor and what workbenches they're using, let's look at a worker's routine. The instruction cycle is broken down into a sequence of steps. It begins with a fetch step to, obviously, get the instruction. Sometimes, the cycle requires an indirect step if the CPU needs to go track down an operand address, basically finding the exact location of the data it needs to work on. Then comes the execute cycle, which takes all kinds of forms depending on the instruction. Finally, we have the interrupt cycle, which allows the processor to pause its current routine to handle sudden, urgent external events. It's this beautifully elegant loop where simple, predictable fetch cycles build into highly complex execution.
Now, what's really interesting about this slide is how you can visually trace data routing through the bus lines during these cycles. Notice how during the fetch cycle at the top, the program counter sends its address to the memory address register. The control unit then signals a memory read, and the fetched instruction travels via the data bus straight into the memory buffer register and finally into the instruction register. It is just a perfectly choreographed dance of data.
But, what happens when an urgent event occurs? So, the crucial point here is that during an interrupt cycle, the CPU can't just drop what it's doing and completely forget its place. Instead, the current contents of the program counter absolutely must be saved. You can see here how the PC's contents are routed into the MBR to be written to memory, often to a system stack. Once the states is securely tucked away, the CPU handles the new emergency before seamlessly returning to its regular work right where it left off.
All right, Section 4, Pipelining the assembly line.
Doing all of this one instruction at a time, that's way too slow. And that brings us to the major upgrade that completely revolutionized our processor factory, instruction pipelining. It works exactly like a physical assembly line in a car plant. Instead of waiting for one product to be totally finished before starting the next one, you break the production into stages. This means new inputs, new instructions are accepted at one end of the pipeline, while the previous ones are simultaneously being worked on further down the line.
And this brilliantly illustrates the incredible speed-up pipelining provides. Look at time slot number 6. At that exact moment, instruction 6 is being fetched, instruction 5 is being decoded, instruction 4 is having its operands calculated, and so on. By overlapping these stages, fetch, decode, execute, the CPU drastically reduces the overall time it takes to process a sequence. It's a massive, massive efficiency boost.
However, as you might guess, keeping this assembly line moving perfectly isn't a walk in the park. Pipelining introduces complications, which we call pipeline hazards. For example, what if a conditional branch instruction jumps to an unknown target address? If the CPU guesses wrong about what comes next, the whole assembly line has to be flushed. That wastes precious time. To mitigate this chaos, modern processors use things like loop buffers, which are basically small, high-speed memories holding recently fetched instructions to help guess the next step and prevent those nasty branching delays.
Which brings us to our final stop, Section 5, Real-World CPUs, x86 versus ARM.
Let's ground all this theory by looking at two rival megafactories powering almost all the devices we use today. When you compare them, you see very different design philosophies. The x86 architecture is famously robust and complex. It features complex status flags, tons of privileged operating modes, and heavy legacy support to run older software. On the flip side, ARM utilizes a streamlined RISC, or Reduced Instruction Set Computer approach. Its instructions are much simpler, much leaner. ARM relies on a uniform array of registers and a strict load-store data model, meaning operations only happen within those registers, not out in the main memory.
Let's move to and see how this builds out in the physical layout of an ARM processor. Notice that hardware unit right in the middle called the barrel shifter? To squeeze extra juice out of their uniform 32-bit instructions, ARM routes source registers right through this shifter to pre-process or manipulate the data before it even hits the main heavy machinery, the ALU. It's just a beautiful example of how ARM optimizes its pipeline to be as lean and flexible as physically possible.
So as we wrap up this explainer, I want to leave you with a thought. The insane complexity of fetch cycles, pipelining, and register management, that is happening billions of times a second right in front of you. Next time you tap your smartphone screen or open up your laptop, ask yourself, is your device running a robust x86 factory or a streamlined ARM assembly line under the hood? Thank you so much for watching and keep exploring the fascinating world inside your machines.